So, good afternoon. I invite you for a fourth lecture of computer architecture skills. And today's topic is about slow memory and how to make it a little faster, or maybe even a fast. If you have a simulator, you can run some practical part even on a simulator. I will show some examples. Maybe it will take a little longer time than it is exactly for the lecture, but I want to have even that generic introduction to the seminaries as a part of the recording. I have there some motivation picture about interesting structure and layering in the mountains. So we start with hierarchy of memories. And the first motivation, we have there two variants of almost the same code. If you look at it, you can see that it is some sum of all elements over the matrix, and one of those goes first through the rows, and then through each row, and then it moves to the next row. Another one is built that it first starts with okay, the first one goes over this one goes this one goes this direction, excuse me. So this one, yes, goes one after another, and this one goes in the columns, as you can see here. Because we first set the column, and then we go through all the rows. And what you can say about such algorithm, which would be a faster? Have you some idea what can be a faster of those two? Okay, the question is in which language it is written. If it is written in the C, then probably the faster one is the first one, because C puts rows one after another. So basically we have element in the row. So in the actual memory, we map rows one after another. So each row is after the preceding row. But if we speak about a MATLAB, for example, then MATLAB works different way. If we have a linear memory, then MATLAB puts first the first column, and then puts another column, and so on. And because we have an actual address space as a linear one, computer has no idea what it is a matrix internally. You only put those glasses which transform the area of ones and zeros to a matrix. Then in the case of sequential access, the C is faster on the first variant of the code. On the other hand, MATLAB would be probably faster on the second one. It is not so simple because there are some optimization and code transformation, and even C compiler sometimes can reorder the inner and outer loop to optimize the accesses to the memory, but the things are not so simple. For sure, for very simple memory, where each access to the memory means to set on the bus the address and then to read a single data, then there is no big difference. But at the moment, when we have ability to access memory by a bigger chunks, then we get into the troubles. So, outline of today's lecture is that we start with the overview what it is memory, how it is little implemented, and mainly to see what it is memory hierarchy. Basically, you cannot have terabytes or petabytes of the memory which is fast and so on. So basically, there is a contradiction between the balance between the price and size and so on. We see the basic memory concept. Then we look how to speed up a memory by adding the cache. So basically, to adding some memory or some storage, which allows to keep data which are fast accessible in the next iteration. And then we see what is this realistic approach and how a multi-level cache memory system works, what it is virtual memory, and so on. So again, we are speaking now about this memory. We hope that our CPU is fast enough to process data so that the bottleneck is not in the processor, but in the speed to access the memory. At the start, there was, in the 80s, 70s, there was sometimes even problem and bottleneck in actual CPU. Then, and the next time, the CPUs, when they switch to RISC technology, has been much, much faster, and the problems start to be a memory. If you look onto some mainboard, okay, this one is a little older, but it is the standard mainboard, then you see, for the PC computer, then you see that there is a socket for the actual processor, and then there are some memory sockets, DIMMs. And then there is sometimes a NOR bridge on the older ones, which controls the memory and provides access to the memory to the processor. On the newer systems, the memory is directly connected to the CPU and controllers move to the CPU. And this is source bridge. It was in the fact the module or chip which integrates another peripherals which are not so fast. Okay, it is disk, SATA, and so on, network communication, but it is not so critical. So, initial architecture of PC computers was that there is CPU in its separate socket, then there is a so-called chipset which has a NOR bridge which controls the access to the memory. Then there is PCI Express bus to the actual add-on cards, PCI Express or some another connection to the source bridge and connection to the peripherals and slower PCI slots. And a fast graphic memory is connected to the NOR bridge. Then, at the time of Pentium 4, there is a more integration that the more stuff is integrated on the CPU, but still we have a memory controller hub which controls the actual memory and connect a graphic. And I/O controller hub, which is for the I/O operation. But it was the initial concept, basically, to have one or more CPUs connected through some bus which allows sharing of the bus between more CPUs to the NOR bridge. There is a memory controller and actual RAM. Then more memory controllers are added in parallel, which allows to interleave the data blocks in the memory, that basically when one of those memory controllers survives data on, for example, odd address, I simplify it, then the second one can serve data on even address or something like that. But this communication has too high latency and it was a bottleneck. So today, most of the processors switch to the solution when we have integrated a memory controller directly on the processor chip. And if we want to have more sockets, not only more cores inside a single socket, but more cores in multiple chips, then we connect those chips with very fast serial communication links, and each of them has its own part of the memory. So this means that we are getting with the PC-grade computers to the area of supercomputers, because it was a common setup even for supercomputers earlier, where we have single address space. So basically, we can access from each CPU all address space in all memory. But for some areas in the memory, we go directly through our memory controller to the memory. And for another area, we need to ask a sibling CPU to provide the access. Because anyway, we see then, or it is topic for advanced computer architecture, how the memory in the caches are synchronized and so on. So in the fact, if you need to add there that mechanism which corrects the synchronization of a coherence and consistency of the data accesses from the CPUs to the memory, then in the fact it is relatively cheap to use it even to provide communication between the chip. And access to the main memory is extremely slow. It takes, the latency is something like 20, 40 nanoseconds, even today on those very fast memories. So at the moment when the CPU needs to actually access data in the memory, then your program is slowed down much. So we need somehow to resolve this problem. Okay, so there is next generation Intel Core 2, which is in the fact predecessor of Cortex Core i7 and today processors. Still, it has a separate graphic memory controller hub, so integrated graphic is part of the chipset, and the processor is outside of this chipset. But then we switch to the today generations or predecessors of today generations, but actual memory controller is moved directly onto the chip of the processor. And we have multiple channels. You see that we have a throughput of gigabytes per second to the memory. So memory, even that main memory is relatively fast if we speak about the throughput, but latencies are relatively long. Then we have there, for example, 40 lanes to access the external graphic and some interface to access the rest of the chipset, which has those small and slow peripherals. Okay, slow peripherals with gigabits per second links and so on. So they are not so slow, but from the, if you compare them with the bandwidth which is necessary between the CPU and memory, then it is a big difference. Okay, so now we return back to a simple model how the memory works. So we have said that the memory is in the fact some array to which we can access the individual cells. And that cell, we can look at this cell as onto the, in the fact, it is same mechanism as the register. So basically, it is some set of the bits, single bit cells, which can be set to 1 or 0 at a given instant of the time if we say now we want to change the value. We have there some address bits which allows to select with which location in the memory we want to work. And we have there some number of A bits, and the number of combination is 2 power A. So basically it defines what is the size of our address space, plus minus. It is not necessary that whole that area is actually backup by real memory. So you can have there gaps where you, if you access to this area, you can get, for example, FFFF only, or sometimes you get a response with the exception that you access area which is not allowed to access, and so on. So, but we can look at it that it is something like that. We have there the actual memory location, and it holds the actual value. So if we look at our processor, then in the fact we can divide our data path and connection with the memory to 2 parts. One is actual data, and the another one is address. That address is controlled somehow by the control unit. Usually it is partially generated by the data in registers, so it is not so strict separated as it looks on this picture. And if we look at the actual memory, then we have there the memory address, memory data, which is that part of the memory which is visible to the user. So where you can store your value or read it back. And then there can be a part of memory which is invisible, which holds some service information. So for example, if you want to build a space shuttle and you know that there are fast neutrons which can flip the information in the cell, then you add some additional bits to each location in the memory, which allow to detect that there is a change and, for example, reset the computer, or you can add there more bits, and then it is possible to define rules how to check and correct the possible bit flip. So it is error checking and correction. You probably know that you can buy DIMMs which are with parity or without parity. So basically this, and you need to decide the probability. Okay, it is sometimes said that even some part of your experience that computer fails or that there is some hard error is not due to the error in the programs. Most is for the error of the program, but some part of this is due to the bit flips in the memory, which can be corrected in some cases if you invest to the memory with error checking and correction, and so on. So we are on the edge of the of those technologies and so on. If we look at actual memory, we can consider the access time, which is actual delay or latency between one request and the time when you can submit the second request. So basically it includes even that recovery of the memory. Then we can count the latency, which is only the time from the instant of time when we ask for the data and when we get the actual data. We usually, for the PC computers and big computers, we usually do not take so much care about the latency, even that it is important. For real-time control, it is very important, but for the standard computational task, it is not so important. And we take care more about the throughput. So this means how much data we can get and put to the memory, and in the fact how many, for example, frames or pictures per second we can process. So we do not take care if there is from time to time some lack of 1 microsecond if the full throughput is in the gigabytes and so on. And for all those parameters, we can speak about the maximum, average, and so on. So this is a possibility how we can quantize the features of the memory. We will speak today most of the time about read-write memory. So this is the memory where we can store data and read them back. And this is usually called random access memory. This has nothing to do with random values inside the memory. It informs that we can select any address which we want for the next access. We can have another kinds of the memory, for example, flashes which are used in your SSDs, has such access pattern that you need to select the block, and when you select the block, then you need to read a whole block. Write a whole block, erase even the erase block, which is much, much bigger. So basically it doesn't allow this random access. We can have a ROM memory, which is read-only memory. Then we can have a flash memory, where a flash memory allows to store data by words or by some blocks, but has a problem that when we want to store a new data, and there are already data stored, we need to erase a relatively big area of that memory, that it is not possible to erase a single individual cell. And the advantage of the flash is that it holds data even if we switch off the power. So it is so-called non-volatile memory, On the other hand, those are volatile memories which lose data when we switch off the computer. And implementation of those read-write memories, which are fast and so on, can be usually by two mechanisms. One is that it is static RAM, which means that such memory holds the data if the power is provided. If we lose the power, probably we lose the data in some time, short time. But when the voltage is applied, then if we select that we have no access to the memory and so on, data are kept inside. On the other hand, this memory has disadvantage that it has 6 or 8 transistors per single cell to address it, to keep the data and so on. So it is relatively expensive. So we use quite often another kind of the memory, and it is called a DRAM, which is dynamic memory, and it doesn't hold the actual data in the bistable flip-flop, but in the capacitor, and we only connect this capacitor to read the data and power the line to charge or discharge the capacitor to change the value. But if you look at such principle, then even if we switch off the switch and keep the capacitor, which has really very, very small capacitance, peak of femtofarad, if we left it alone, it starts to leak the current. So after a relatively short time, you cannot distinguish if there initially was 1 or 0. So dynamic memory is cheap. It has only a single transistor per each cell. Actual cell is implemented as a capacitor, but it requires a refresh. So basically, once per, for example, 60 milliseconds, you need to read all the data and write them back. For sure, if you want to read them through the processor and write them back, then you would lose all the time on the refresh. So it is done directly in the memories, but they need to activation of those cycles, which allows them to refresh. So, but for the higher capacity, we usually use dynamic RAM, and usually this S in this case has nothing to do with this one, with this static, but it is in this case called a synchronous dynamic random access memory. So this means that it is synchronous with the clocks that not only control signal, but even the clocks are applied and actual data are delivered according to that clock. And the access pattern is relatively complex. You need first pre-charge the lines where you want to read the data from SDRAM, and then you get the data. You'll get some row, which is relatively long. You can select some part of this row to deliver it to the CPU. Then you need to do the actual refresh. And if you have a row, so basically some block, then you can read the neighborhood values quite fast because they are in that output row. And at the moment when you go to next row, again there is a long time which needs for the pre-charge and so on. So it is the access pattern is very important for the speed which you get a data. So even if you do not use a cache, which we get later. Another problem is that at the start, the CPU core was relatively slow. There was even the time before the 80s when it seems that speed of the memory has increased quite a lot, so it looks like there is no problem with the memory. Then there was a time when CPU started to be relatively fast and process instruction faster. Then there was a rapid increase of the throughput of the CPUs by switch to the RISC architectures. And at that time the memory didn't keep with the speed change. So basically it was main memory starts to be total bottleneck, and it was necessary to find a mechanism which allow sometimes or at most times to speed up processing. Then today there seems to be a slowdown of the processing power increase on the single core and even on a whole processor chip. So today the thing starts to be a little more complex, but memory still is relatively slow. Okay, there are some ideas, only to have some idea about the sizes. So this is area of SDRAM and RAM. For some technology today it is even faster. And now we look at a bubble sort algorithm. So it is what you should prepare for today seminar. We have spoken about bubble sort at last one. And if we look at the bubble sort algorithm, so what happens there? We have there some array, this one, and we compare a neighborhood elements and check if we should swap them or not. And we go forward and forward. So basically first time we check those two, then we move and check again those two. So basically we reuse the values which are neighborhood. And after some time we get at the end and again start from the beginning. So we can see that this algorithm, which has some complexity equal to O n square or something like that in the worst case, because there are two loops from 0 to n minus 1. Then in the worst case is there this complexity, and it accesses in the fact each location in theory the n, 2 times n or something like that. So we can say that if we can somehow speed up access to the neighborhood elements in the memory, then the actual throughput of this algorithm would profit. And if we can keep all data and reuse them again in some fast memory near to the processor, then again we can get a gain on the speed. So from this observation, we can define that there exist two principles which can help us, and it is a so-called temporal locality. So this means if we have worked with some variable, there is relatively high probability that we will reuse it again, that part of the code is active and that variable will be required and processed again in the short time. And then we have the another mechanism or another observation, and it is spatial locality, that basically if we work with the vector and it is some longer vector, then there is a high probability that if we work with it at the address A, we will work with it at the address A plus 1 or maybe A plus 4 or even A minus something, but still we will work at some address near to the address which is processed. Same for the instruction. For instruction, it is even more clean, basically. For the instruction, we know that program interprets the instruction sequentially until some branch. So we can reuse this mechanism and define that we try to keep those often used data in some smaller capacity memory, which is faster. And then we will have there some another slower memory. And now we look at the whole memory hierarchy. So we can speak about the main memory. Then we can speak about the secondary memory, that if the data do not fit in the actual RAM, then we store them on some disk, SSD, and so on, where they are not directly accessible by the processor. So that is the reason why we call this memory a secondary storage. We can then build a virtual memory which allows to use that secondary storage even as a part of the address space of our process. And we can copy those blocks which are often accessed, from the disk to DRAM or from the DRAM to some faster memory. So in the case of DRAM, because it is again too slow, we have there some SRAM memory which is near to the CPU and which is much faster. And we can sometimes even move those variables which are actually processed to the registers of the processor, because as we have seen, registers are directly accessible by the processor, and it is the most fast memory which we have. So if we look at it as a hierarchy, then we have there the actual processor registers. It is very small area, 32-bit values, so not so much, but it is very fast. So in the code, if we put there local variables, it is the win. Then we have there that main memory which defines the area which we can work typically in the processor, but it is slow, so we put there some intermediate memory which is called a cache. It is same for the access of web pages. You know that if you access a web, then you have some cache in your browser, and basically if you access again and again same page with the same pictures, then even if the page is changed, then probably the pictures are kept in your cache, local cache, and you do not need to access them again. So it is exactly the same principle. Those principles, if you look at them, are used a generic way through whole the IT systems, not only in this hardware-oriented part, but okay. Then we can have some non-volatile memory, because as you have seen, those memory needs a power, and when you switch off the power, then you lose data. Then we can have there some flash on the USB or maybe SSD and so on, a hard drive or SSD, and then if we do not fit into this memory, we can store the data to some tapes. You can have a robotic system to store the tapes and so on. For example, GitHub sources has been transferred to the microfilms and are now stored somewhere on Spitzberge under the ice, either the glacier somewhere. So it is the way how you can back up data, but the access time to those containers and so on is not fast. So, okay, so as you can see, each level is slower and slower. If we look at the actual system, then we have there our processor. It has registers which can be accessed very, very fast. Then it has a cache and the main memory. And the control of data which are present in the registers is under the program control, programmer or compiler. What is in the main memory is again controlled by operating system and your program. But because you do not want to take care about each access and check if the data are in the cache or are not in the cache, then for this reason the cache is a so-called hidden memory which is maintained by the hardware for you. And then under the control of processor we can store the data to the disk, okay, usually not by byte, but we instruct operating system to set up some DMA transfer which copies data from the memory to the disk, but we need to issue some operations from the processor basically to say this block of the data should be sent to the hard disk controller. We can have some slower read-only memories, for example, for DVDs and so on. We can have those even slower robotic controllers with tapes and so on. And important is, again, I repeat it, that what is in the registers is under the control of the program. What is in the main memory is mostly under the control of the program and operating system. But what happens in those memories in between, those caches, is done partially automatic in the hardware, or mostly automatic in the hardware. The reason for it is that the management of so many data in the cache and checking and so on would mean quite a lot of the code, and it would be slow. And we cannot even build a large and fast L1 cache, because even that is a problem. So basically we usually have some small memory which can access data in 1 or 2 clock cycles when there is a request from the processor. And then we have a second level which is larger but slower and usually used for multiple cores. And then we have that main memory. And at the moment when we want to access those data as if they were in the main memory, but we need to check if they are present in the cache, then there has to be some mechanism how to check and keep the track what is actually in the cache. So in the cache we do not store only the data, but we need to put there some additional information which allows us to check if the data from the given address in the main memory are present in the cache, and if there is data are missing, then we need to find a free location or long time not used location and put a new data there and put there a tag which informs those data are from this area from the main memory. So basically we need somehow to swap data in the cache between the main memory and cache, and if there is a hit, so basically we find the data in that faster memory, we do not need to invest a long time to access a data in the main memory. If there is a miss, then we usually copy data from that slower memory to the faster. So the solution to the problem of the main memory, this concept of the caches is used in the access to the web, in the some complex computation and so on. So basically you can have the cache of typical results of something, or you can have pre-cache it, for example, the database. If you have many queries, then you have the production database, and for the users and public which want to access the actual data, you can have a read-only copy which is in the fact cache of those requests which are sent often to the server and so on, to basically to lower the load of the server. But now we focus what is done with actually that main memory. And in this case it is again the cache, and in this case the cache is maintained transparently. So automatically if you access the address in the main memory, then it is checked if the data are in the cache. If not, you access the main memory and data are stored in the cache memory. And in this case, we need to use some size of the block. We usually do not store those blocks on the basis of individual bytes, because for each of that bytes, we would need to keep that additional information from which address in the memory we have took that actual byte. So in such case, we would waste too much hardware for a small useful value of the cache. So for this reason, we keep data in some bigger blocks, and for each of those blocks, we need to keep a tag to remember from which location in that bigger memory the data are taken and kept here. And then we need some flags. Those flags allow us to check if the actual location is filled with the data or if it is empty and so on. And if we take all the location in the cache, so capacity of the cache is this part, but we need to add those additional hardware there, then if we want to take all the locations equally, So to be able to store any external address from the main memory to any of those rows, then we need at the attempt of the access to given address to check all those rows if there is a match between tag or not. And if there is a match, then we know, okay, there is a hit, and in this case, we take the actual data from that row where is a hit. But this is quite expensive. So this is called a fully associative cache, which allows to store arbitrary address into the arbitrary location of the cache, but it is expensive. Okay, it is possible to have a lower number of comparators, but in this case, we would need to sequentially go through one after another row, and it would be again slow. So this is expensive. And we transfer data on the block basis. So basically, if there is a miss, then we copy a whole block of usually 8 up to 1 kilobyte from the slower and bigger memory to the cache. Typical size of the block is today, it was 32 bytes. Today it is more even on the small ARM CPUs, 64 bytes. But some system has 128 bytes for the block, and it is possible to have for supercomputers and so on, even bigger blocks. So, if the data are present here in that memory, which is fast and near to the processor, then we say it is a hit, and we compute a hit rate. So basically, if you compute all accesses from the CPU to the memory, and we know at how many cases we get a data from the cache, then it is called a hit rate. The rest of those accesses which has to go to the main memory are called misses, and because a total number of accesses is sum of those two, then the miss rate is actually 1 minus hit rate. And what is the important parameter is the penalty between the access to the fast memory and then if we do not find the data there, to access the actual data at the main memory or next level of the cache. So it is called a miss penalty this time. So again, hit rate, the number of accesses which has been fulfilled by the cache. For sure, this value is not given for a given design of the hardware. It is a combination of how well is written the code, how big is data set, and what is some probability of changes in the data and so on. So hit rate cannot be theoretically computed for unknown load. So basically you need usually to use some load and test for actual data and some benchmark what is the hit rate, miss rate, and then you have there this penalty. So at the end, what is important for your program is average memory access time, because sometimes it is slow down, sometimes it gets the data faster, but for the standard computation, if it is not something in the real time and so on with deadlines and so on, you usually want to know this value. So basically it is equal to the time to find a data in the cache and to get a data from the cache if they are present, plus a miss rate. So at how many times we need to go to the next level of the cache or to the main memory, and this time this count of accesses is multiplied by the miss penalty time. And we can extend it. It can be a hierarchic. We look at it a little later. So there is a simple case. We have a miss hit rate, hit time is 1 cycle. Memory access time is 8 cycles. And we know that for our actual load, 2% of the accesses has to go to the main memory. So we compute it, and we find that even that the main memory is 8 times slower than the cache, then in the fact our average access time is almost the same as for that small fast cache which is used. Okay, we have luck at this concrete case. And okay, important is that we need to keep there a tag, because we need to know with which value data corresponds in the main memory. And we need to add there some comparators and to check that each line has, if it has or doesn't has the matching tag for fully associative memory. But the amount of the hardware which you need to add to this cache to check for those matches is too big, and for this reason we usually do not use a fully associative cache. So we somehow try to simplify the hardware that we have there, for example, only single comparator in the directly mapped cache. And when a CPU writes to the main memory, then we need to keep some data consistency with the peripherals and another CPUs and so on. It is out of the topics of our subject, but you should know that there is this problem, that basically if you have two threads and those access data from two cores, each running its own program, own thread, then there can be a problem. And there would be no problem if all data are write through to the main memory. So basically at the moment when we change the data, if they are present, the change data in the main memory. And okay, if that another processor can check that data has been changed in the main memory and access the change data instead of those data in the cache. But it is not the case, because it is slow to write the data to the memory. In the fact, the actual data writes to the memory are usually through a write buffers, because your program and algorithm is blocked when the data are not present which are read. The writes can be postponed in the theory if there is not problem with coherency, consistency, and so on. So basically, there is an attempt to put data to some write queue, and until it is full, then you do not need for the finishing of data writes. If the data are lost from the cache in between, then you can use even that write queue again to provide the data to the CPU. One option is that we have only there a write-through mechanism. Another option is that we keep the data in the cache, and if we modify the data in the cache, we do not issue the write, but we modify data only in a given cache line in the cache. And keep the modified data as long into the cache as we do not need a given location for some new data. At this moment, we need to add to each data block in the cache, we need to add not only tag to know where data has been taken from the main memory, but we need to add there some additional bits. For example, the dirty bit, which informs that given line, given row in the cache is already changed. And then we have there that flag which informs that there are valid data at the given location. And at this moment we get to the trouble, because we have some capacity of the cache, and very quickly we use a whole capacity of the cache to store data. And at this moment we need to find which data we should release from the cache and use that location in the cache for a new data. And the mechanism how to select which data are probably not necessary in the for the computation in the short while in the future is called a cache content replacement policy. And we can do a random replacement. So basically we randomly choose, okay, this line will not longer be used. We can try to find the least recently used, which is most common algorithm. So basically we look for the data which has not been used in the computation for a longest time. Because for those data which has been used in the previous iteration and so on, and are in the fact often accessed, then those probably can be accessed again. For some cases, this algorithm doesn't work so well because, for example, if you have multimedia data and you read the multimedia stream, then you probably read it only once. So such data are not necessary to be kept in the cache for longer. So there are a mechanism how to inform the cache that some data should not be cached and so on. But generally, this algorithm works quite well. The least frequently used has a problem that if you have there some data which are not used often, but are used from time to time, then those data can block, with the accumulated number of accesses, can block their replacement by the data which could be used more and which allows to have the cache more efficient. So this algorithm has problems. So usually if you want a least frequently used first, then in the fact it is combined into some adaptive replacement cache theory and system and so on. And okay, we can decide if we have a write back or write through. We usually want to have a write back. This means that we keep a modified data in the cache and we put them to the main memory later. And there is a mechanism, okay, we are speaking about Hennessy-Peterson book. So this is what Professor Hennessy done on the MIPS architecture. So they have two caches, and they decide that the access pattern for the instruction is different than the access pattern for the data. So you sometimes have small amount of the code which works with large amount of the data. On the other case, you can have small amount of data which is processed by the complex algorithm. So they decide that they are separated caches for instruction, in this case 16 kilobytes, and for the data 8 kilobytes. And then they go to the same system bus. So in the fact, main memory is for Newman, but the actual caches are separated for the instruction and data. And there are some examples how we can use capacity of the cache. So at this moment, we start with the cache which has capacity of only 8 blocks. It has block numbers from 0 to 7. As we have already spoken, the fully associative cache allows to find a block which has data which are probably least useful for the future computation, and select an arbitrary block for a given data. But problem is that in such case, we need to check the address with all the data blocks. So for this reason, we quite often use a much simpler, for the hardware, a directly mapped cache, which allows to put a data exactly to a single block according to its address. So basically, data address specify to which block we can store a data. And we cannot store data from a given address to any other location. So for example, if we have address 12 and we have 8 locations, we divide address 12 by 8 and we get 4, and it is only location where we can store a given address. But this doesn't work as well. It doesn't work too well as well. So we usually use a compromise when we have a 2 or 4 or 8-way associative cache. This means that we divide the blocks to some groups. In this case, those groups are called the sets. And each of those sets allows to store data from some range of the memory, according some rules. And usually it is done such way that data are stored not according most significant bit, but by the least significant bit. Anyway, now we look at the directly mapped cache. It is simplest for the hardware. We do not need a comparator for each of the rows, because we know that for given address, the data are present in the given row or are not present at all in the cache. So basically how it works, in this case, if we have a capacity 8 words, and we speak not about bytes, but about the words, so it is 32-bit value in this case for 32-bit computer, then the number of sets, the locations where we can store data according to the address is 8 still, and we use two least significant bits address the actual byte in the memory, but as you have seen, load word instruction and so on do not take care about bytes, so we can say that those last least significant bits are 0. Then we use the next 3 bits from the address to select which set and which row actually can hold a given address. And then we take the tag from a given row and compare it with the rest, with the 27 bits, because if we compute 32 minus 2 minus 3, we get this value, 27, and check if there are data present or not. So basically our parameters is capacity, 8 words. The number of set is in this case equal to the number of blocks and to the number of sets, so it is 8. Size of the block is 1 word, and we have only a simple cache. But in this case, we can get easily to the problems. I try to demonstrate it later. And there is how we can decide how we select to which row we store data in the cache. So if we have there a cache which has 4 rows only, and we can decide that we will use a most significant bit from the address to store the data into the cache. Then data from consecutive locations will go to actually the same row in the cache. But it is typical that we access the array in some area or some matrix and so on. So in this case, we would use only a single row of the cache when we work with those data here. And it is not so typical that we work with data on so much random places in the memory. So it seems that it is better to use interleaving. So basically, if we work with some such area, then yes, this maps here, and so on. And we can keep a whole data set in the memory up to the capacity of the cache in the fast memory. And okay, if we have there some additional accesses, then those start to trash the cache. Basically, we lose the data, those data from the cache when we access those additional ones. And okay, then there will be a more or better, more colored picture. So basically, we have there that 8 locations in the cache. Then there you can see the actual addresses, and you see that to know which data are in the given row, then it is enough to keep in the fact the tag which is only of 2 bits in this case. Yes?
On the previous slide, the middle order, wasn't that the least significant bits or no?
Those was with the most significant bit.
The middle order one?
Yes, yes, this with most significant bits.
Yeah, I'm saying for the middle order one, is that the least significant bit one?
Okay, okay, it is called, okay, middle order, okay, it is least significant, basically those two least significant bits which informs which byte in the, or which bits in the blocks are used, then in the fact we do not care about them at this moment. So for this reason, it is called middle order, So basically, from the rest of the bits, which are in the fact least significant bits, define where to store it, but some part of those least significant bits is ignored at all. We will see it later. But yes, it is good catch. It is, okay, middle order. Okay, I think about this that it is in the fact 0, but you are right that we can say that it is middle order. Or it is correctly written here, but I have... Okay, so in the fact, in this case, we have there the index. Index is given by those least significant bit or less significant bits, and the tag is given by those two most significant bits. And there is a problem that a data from different location maps to the single row. So what is the problem? At the moment, when you have, for example, two arrays in the memory, I will try to demonstrate it, and you want to add the contents of one array to another, and you sequentially go through one array and through another array, then if they start on some random location, then usually you get this array into cache, that part, and this array part which you work on into the cache. But at the moment, when those two arrays start at the addresses, where the difference is a multiple of the size of the cache, then at that moment, data starts to map to the same location in the cache, and at the end, instead of the speed up by adding the cache, you have a slowdown, because you are even slower than if you have there only the main memory, because you add there 1 or 2 cycles to locate the data if they are present in the cache, and in each case you find another data which you do not want for this access pattern. Okay, so real organization and real system use exactly the valid, dirty bit, and so on. There are some additional information about the sharing and so on. It is not so important. We usually, even in the case of directly mapped cache, do not store the individual words, because to keep for each individual word a whole tag and another stuff would be too expensive. So for this reason, we usually store into the cache a whole block of more words. It has another additional advantage, that the spatial locality says, okay, if we access this word, then there is a high probability that we access the neighborhood word as well. So when we have the miss, then we take together follow-up words, and there is high probability that those will be need in the next cycles. So for this reason, it works this way. And we can say, if you look at the address, we, in the 32-bit processor, we do not care about the two least significant bits. It is byte in word. Then we have there some set of the bits which select which of the word from the block we want to use at the time of the hit. Then we have there a sum set, in this case 12 bits, which select one of 4,096 rows, in this case. And to check that actual data at given row, which is selected by those bits, actually are data from a given address, we need to compare a tag which is 16 bits in this case. And it is directly mapped cache, because all data have only a single location in the cache where we need to check if data are present. But in this case, we have problems with the collisions. Okay, I can switch to the demonstration, but I think that I switch at the end of the lecture or at the start of the seminar. So For this reason, that there can be collisions in the cache, we usually want a more way set associative cache. So in the fact, we divide the capacity, for example, for our initial 8 rows, we divide it into the 2 ways, each of 4 words, and we put in this case, the pairs of those rows in the fact into the sets, and we select the set by 2 bits at this moment, not 3, because that third bit was for the case that we have 8 words. We have there only the 4 sets. But in this case, if there is a collision, so basically if we work with 2 addresses which are mapped to the same row in the cache, we have the chance to use another way for those data. And when we want to check if data are present, we need to get a tag from the one way, second way, and other 2 comparators. And if one of them provides a hit, then in such case we know the data are present, and we select according to the hit. Here we select which data will be provided to the processor. And as you can see, in this case, we map blocks to 2 locations. So even that capacity is 8 of the cache, then in that basically mirror of the capacity of the cache in the main memory, we map 2 locations to the same row, but we have 2 ways. So basically there is some access pattern. So if we access the address 0, then there is a miss. We try to access the address 32, but we have found that this way has been used in the previous access, so we do not kick out those data, but we put data there. And then if we access 0 again, we have a hit, because data are still present in the cache. Then we try to access 24. 24 maps to the different row, so there is no problem, to the different set. Then we access again 32, and still data from the 32 are present. So we access and divide and distribute the capacity of the cache to the accesses reasonable way. At the moment, when we access a value at the address 64, then it again maps to the first row, first set. And in this case, we have no other option than to kick out one of those locations. And because the least recently used was the address 0, because the last access was to 32, then that access to the 64 would kick out that copy of the address 0. And we can have n-way set associative cache. So for example, 4-way, and again, at the moment when we have 4-way, then the capacity is distributed to the 4 ways. So 4 times less rows. So in this case, we have 8 bits to access the row, and 2 bits to select the byte, and the rest is compared as the tag. And at the moment when there is a hit, then can be the algorithms and mechanism of replacement of the values in the cache ensures that hit would be only in the single way, and we can select those data from that way and use them. Yes, we in the theory would be happy to have a fully associative cache, but it is a problem because for each of those elements we need a separate comparator as we have at the start, and it is too expensive, so it is not used. And we need to compute some statistic, because you need to decide if your money and your hardware and number of transistors is used efficiently. So basically what you do, one option is that you know the actual workload which you will use, and you can benchmark the actual and simulate the data access pattern for a given real program. Or other option is that there are a typical benchmark which somehow mimic typical computation and the office application and scientific application and so on. And one from those is that Spets 2000 benchmark, which is quite often used. And in this case, it is actual measured values for some processor, and you can see for sure when we have a bigger capacity of the cache, then the number of misses, the number of accesses of the external memory is much lower, for sure. But at the moment when we have a capacity of 1 megabyte for L1 cache, then we cannot build it fast enough, and it would be extremely expensive to put it on the chip in this case. So basically they decide that it is too much. So we try to lower the size of the cache, and basically we see that the actual throughput, thanks to the ratio between the miss penalty and so on, starts to be critical somewhere here. So they decide, okay, something like 32 kilobyte of the cache is what is typically necessary for those applications. And then we can check. We can use, we know how big size of the chip we need to use for this cache, and now we can test what happens if we divide that capacity to the multiple ways. And you see that by switching from the directly map it, so one way, in the fact directly map it means that we have only one block in the set which can be used for a given data. Then in this case, we have relatively much higher miss rate, so we probably want to go at least to two-way associative, because that way we have in the fact, if you look somewhere here, then we get something like 20% speed up from this one. For 005 to 004, it is in the fact something like 20% speed up. So it seems that it worth to add there a little more complex hardware, and in the fact we have small decoder for 1/2 of the rows, so it can at the end be of same complexity. Then we can try to add the 4 ways, and you can see that there is some small change here in the number of the misses, some small another decrease. And when we add 8 ways, then in this case there is a relatively very small gain. So we can say, okay, in this case 4-way cache about 32 kilobytes is a good choice. Another problem is how big a block should be. If we have very small block, then there is a bigger overhead of amount of the management data of those tags and so on. It is one problem. And another problem is that if we have a small block, then we do not use a spatial locality so well. If we have a bigger block, in the fact, if we can have a block which is of the size of main memory, and at the first time when we access that block, we copy everything to the fast cache, then it is the best option. But we cannot have so fast and large memory. But if we have a block size which is of some reasonable size, for example, if you want to work with a point data structure, then for sure, if we have a block size which takes together x and y values, then you have the advantage because you usually access the x and then y. So if there is a miss on x, you get a data for y automatically into the cache. So for this reason, if you have too small block size, you probably have higher miss rate. On the other hand, at the moment when the block size is too big, then at this time you quite often pull into the cache a data with some rest of the memory which you do not need at the next iteration. So basically you kick out another data because capacity is limited, which could and have a bigger potential to help you if they were kept into the memory. So for this reason, if you have too big block size, then you have a trouble. So there is a graph where you have a block size from 16 to 256 bytes, and analysis if you have 4 kilobytes of the cache, 16 kilobytes for sure, 16 kilobytes is better, but problem is that you cannot have, for example, at that time 256 kilobytes of fast cache. It would be a best, but problem is that you have problem to implement it. So basically they decide to go to something like 16 Ks and block size 64 bytes. And again, this is the slide and measurement from that advanced book. You should use there the standard book, hardware software interface, but then that quantitative approach was relatively revolutionary book, how to analyze these things. And this stuff and processors and so on. So there are some optimizations. If we have a larger block size, we reduce the compulsory misses, so those which are given by the access of the neighborhood element or sequence of the locations in the memory. But we increase the other misses because we kick out, we pull data into the cache which are of no use sometimes. If we enhance the cache size, then we reduce a number of conflicts, misses, and so on. But we increase hit time and power and the cost of the cache. So again, you need to keep this in the balance. If you increase the associativity, then again it helps to reduce the number of the conflicts, but increase the hit time because the logic is more complex and more caches in the fact those ways are addressed in the parallel and more comparators works in parallel. So again, you lose the power. So the resolution is not to make the cache too big, the L1, but have there another level and reduce the misses in the L1 cache by the slower but bigger L2 cache. Another thing is that we want to prioritize reads misses before the writes, so writes can be postponed in the that write-back buffers. And another problem when we have a virtual memory is translation of the virtual memory to the physical one. It is a later topic. So we have a multi-level cache, and in such case we can then enhance and speed up the accesses, because if the data are not found in this small L1 cache, then we have their L2 cache, and if they are not found in the L2 cache, which is usually common for the data and instruction, then in such case we can ask the main third level, last level cache, for example, in this example, and it is a single cache, but implemented as multiple blocks, and it is common for all cores. So if we have there Intel Nahelm core, then we have there 4 cores, and each of them has its own L1 cache, L2 cache, but L3 cache is common for all, which advance even the communication between the cores, and which advance even the checking which data are accessed which core if we have multiple sockets. And there is some idea to know something about timing. So basically we have seen a processor, we will see a pipelined version on the next lecture. So basically there is our processor which can execute instruction very fast. In the fact it can decode up to 4 instructions, or sometimes today up to 8 instructions in parallel, but okay, it is still out of scope of our subject, so it is superscalar execution when we can execute more than single instruction in the single clock cycle. We have there a L1 cache for the instructions. It is relatively small, 32 kilobytes, 4-way associative. Then a data cache, again, it is in this case 8-way associative and 64 case. Today, the Intel has even stepped back to the 32 kilobytes of the, no, it is 32 kilobytes, excuse me, 32 kilobytes and 64 bytes in the block, 64 bytes in the block, it is same here. So, if the data are not in the L1, then we access the L2, which is 256 kilobytes, and we have 8 megabyte L3. And what it happens if we do not find a data in the L1? So access to the L1 latency to get a data from the time when we issue for the execution the actual instruction to read a data is 4 clock cycles. It is relatively fast. But at the moment when we do not find a data in L1, then we need to add another latency of 6 clock cycles. It is same for the instruction, same for the data. So at that moment, you have latency about 10 clock cycles. And at the moment when you do not find the data in the local cache, L2 cache for a given core, then you need to access the data from the common L3 cache. And there can be a collision from the accesses from multiple cores and so on. But anyway, even in optimum case, you get a penalty of next 25 cycles. So access of the data from here is something like 35 to or 40 cycles. And at the moment when you need to access the actual memory, then it is another 100 cycles or even more additional cycles, the latency. So you see how it is important to write algorithms such way that they keep the data in the L1 cache, because if you access actual data in the main memory, then you are 25 times slower or something like that than if you fit into the cache. And almost no compiler, no high-level language helps there for you, basically. It is the property of the algorithm, and you usually need to think if you want to write a high throughput code, what to do. There are some interesting things about the cache. For example, the L3 cache in this case is 16-way and is inclusive. This means that if the data are in L1 or L1 or L2, then each such data are still kept in the L3. This advantage that if you need to kick out data from the L1, that you do not need to read the rest of the data somewhere or allocate the block. Basically, you know that there is still a copy in L3. It has another advantage that you do not need to check a whole hierarchy of the caches if some another processor checks if the data are in the cache or not from some another chip. So this is the reason that we have there the inclusive cache, that all data which are kept in L1 or L2 are available here. On the other hand, L2, for example, in this case is not inclusive, so this means that if we copy data from L2 to L1, that we basically can swap the lines. Okay. We have there some temporal store buffers which can keep data before they are actually written into the memory. And we have there some translation look aside buffers which are used for address translation for the virtual memory. And if we look at two-level system, or it is two-level system in this case, only Pentium 4, so not three-level caches, but only two levels. L1 has access time 2 cycles, L2 19 cycles, and actual memory in this case 240 cycles. Then if we have 5% misses in L1, and L2 has 25%, but from those 5% of misses in the L1, then we can compute the actual miss rate, in this case as 2 cycles for the L1. If we do not find their data, then this is the number of accesses which need the additional 19 cycles to access L2 and check if there are data. And from those, each fourth access, in the fact, needs to access the real memory, and it takes this time. So at the end, we get to something like 6 clock cycles for given load of the data. But it is not so horrible if you look that the actual access to the memory without cache would be 240 for each access. So we have speed up. So advanced optimization, small and simple L1 cache. There is some mechanism to predict way and what will be a next access and so on. Then we can have pipeline solution, non-blocking caches, that if there is an access and there is miss, that the CPU start to process next access to the memory and didn't block on that access which is still not resolved. So it is possible sometimes to reorganize the code. Another possibility is a critical word first. So if you have, for example, 64 bytes or even more bytes into the cache line, and the actual width of the access to the memory is narrower. It has, for example, 64-bit only, so 8 bytes from that 64 bytes. Then it is advanced that you can start to access and fill the cache not from the first, okay, it is not word, but first, it is not block, what it is, basically the width of the memory, but that you start to fill the given line from, for example, byte 16, then you fill those bytes from 24, and then you restart and fill from the start of the line. Because for our two-ray caches, it is necessary to read a whole cache line from the memory, and if you modify it, it is necessary to store the whole line. It is not possible to store only the part. But if you need to access a word which is in the middle, and you start to read the data from the beginning, then it has some latency before you get to that critical word. There is some mechanism that if you have more writes and they somehow overlap, that only they are merged in the write buffers. So basically we minimize the number of writes operation. And there are some techniques even on the compiler side that you basically can, for example, swap the inner and outer loop if the final result is not changed by this swap. And we can add there the prefetching. That basically software can say it is high probable that those data from this address are necessary in the next computation. And CPU and hardware then decides and tries to fetch those data, even that you do not actually read them, so it doesn't block the CPU. And some another hardware is there which predicts and finds that, for example, if you sequentially access the location in the memory, that it starts to prefetch following locations. Okay, and there are some another possibilities how to do that early restart. When we, for example, early restart means that we do not block the processor if we already have the word which is necessary for our computation. Requested word first, again, it is that reordering. If you do a write, you need to first fetch a whole block and then exchange the actual value. But you could delay the fetch and store somewhere the information that it is necessary to modify the word and so on. We can recouple the indexing to the cache and hit detection and so on, increase the associativity. We can increase the branches and so on. So there are possibilities how to find and predict what will be necessary. Hit under miss and miss under miss. This is that we do not block on the miss of the access to the cache, and basically try to execute the following instruction and then return to the instruction which was blocked on the cache. We can have multi-bank caches which allows parallel access to different bank, to even to different locations and so on. As for the DD-RAM, it is necessary to look at it that it is in the fact array which has some columns and rows, and the actual addressing works such way that we first send a row address, we select the address, then we fetch a whole row from all those small capacitors, then we select the column and access data from a given column. And then we access not only a single word or single width of the RAM, but we have usually there multiple clock cycles and access the whole row or whole area. Okay, so it was very quickly what it is cache and how it maps to the memory, and I try go very quickly through the virtual memory. Why we need a virtual memory? Virtual memory has two main use in the computers. Initially, it was called a virtual because it allows to extend the address space for a given process to have a bigger amount of available space to work with than its actual size of the physical memory. So virtual, something which is not existent or it is only in our mind. And it works such a way that we map a physical memory to some bigger address space of the processor or process. And when we access the area which is not backed by the physical memory, then in this case, we put some part of the physical memory to the disk and use some another area of the disk to keep the contents which we can swap in and work with that area. So basically, instead of keeping, basically it works similar way like a cache between the main memory and the CPU. But in this case, it is that the physical memory is cache of some simplifying bigger address range which is on the disk. For example, in some file, swap file, for example, from Windows, maybe you can know. And so we can work with that bigger amount of bigger data set at the expense that if we access that part which is not actually available in the main memory, then there is an exception, and we need to use services of operating system in background, which ensures that it swaps data which are, for example, modified in my memory, put them to the disk, and swap in some another area. For sure, it is slow because access of the disk means to, in the case of rotating disk, there is something like 24 milliseconds to access the given cylinder, then to read the data and so on. So things starts to be much, much slower. But you can work with the data set which cannot be used in the preview system. And the mechanism is implemented such a way that there is some unit which is put between the actual processor. Processor works with that virtual address space, and this unit maps those addresses to the physical memory cells, or maps and informs that a given area is not present. So it was the initial idea about a virtual memory. The another, and today even more important reason for the virtual memory and address translation is that we want to separate multiple processes which are running on the CPU. So we can have there multiple processes, and each of them has its own view of address space. So basically a virtual memory or virtual address space, and cannot access and see a data in another process address space. So this separation and security is very important. And even these mechanisms allows to separate the operating system data, which are not accessible to any of the processes. So it allows to mutual separation between processes, separation of the processes and user code, that it cannot access system data and so on. So it is another use of this mechanism. But the actual translation is relatively slow. So basically, we divide our virtual address space to some blocks. Again, if we have for each byte in the memory, if we want to have there a point, or for each byte in our virtual address space, if we want to have there a pointer where it is located in the physical memory, then again, the management data would be much, much larger than the actual data which we want to work. So mechanism how it is done through some table. So basically, if we have there that 8 bytes virtual address space, then we take that 3-bit address. 3-bit address looks into some table, and this table selects which physical address backups a given virtual address. So for example, for the address 5, we can find that that location of the address 5 should be, it is, yes, this goes this direction, it is there, 7, so basically this maps the address 5 to the physical address 7. But if it is on byte-to-byte basis, then basically we need the sizes of the tables, which is extremely large. So for this reason, we divide a virtual address space into some pages. We call this a page, which is some number of bytes. And we do not remap this to the arbitrary location, but we remap it to the same size frame of the physical memory. So we have virtual address, it is divided to the pages, and the table only maps given. For example, in this case, it is the page 1 in the virtual address space to the physical 2. So it is the 1 maps to the 2. So table is much, much smaller. But anyway, even in this case, if you, for example, decide that typical size of the page today is 4 kilobytes or 8 kilobytes, or maybe 16. Apple M1 has bigger pages, which is quite problem to run Linux on that CPU, but it is somehow resolved. So basically, we can have a different size of the pages. For sure, at the moment when we have too big pages, then we start to waste some time part of the page and so on. But the amount of management data is smaller and so on. So it is again some compromise. But Intel and most of the ARMs use 12 bits, so 4 kilobyte pages. And in this case, we have 20 bits which we need to translate from the virtual page number to the physical page number or to the physical page frame. And even such table which has needs to translate 20 bits, what is the size of such table? We want to translate 2 power 20 combinations to the 32-bit addresses which points to some locations. So it is 4 megabytes. 2 power 20 is 1 million. But for each location we need 4 bytes. So we need 4 megabytes, which is quite large amount of the data, which we need to keep in the memory, only to the mapping. And if we have more processes, then we need 4 megabytes each time when we start a new process, which is relatively large amount of the data, and typical process doesn't use all 4 gigabytes of the memory. So for this reason, we usually do not use the single level page table, but we use multiple level page tables. Okay, so I skip this. And for this reason, basically, we usually divide the page table at least to the 2 levels. So there is a computation that it is too big area. And for example, for 64-bit system, if we have that it would be 52 bits translated in one go, then you do not fit with such memory and such table, maybe even in the Prague or some big area in the world. So it is necessary to do something with it. On 62-bit computers, usually only 48 bits of the address are valid, because we usually do not need more bits, valid bits of the virtual address. Maybe today there is an extension to 52, I think. So the typical setup for the Intel is that we keep the offset of 12 bits, so basically 4K, and then we put there levels where we start from the most significant bits in this case, and in this case they decode 9 bits as an index to the top level directory of the page tables. And for each process we have an address where a page table for a given process start. And then we find that the next level of page table is on this address, physical address. Basically all this, in the fact, we have it there as a hierarchy, but in the fact, the page directory base register, in the fact, points somewhere into the memory where is this top level page directory. So that we have it written here and shown here on the picture on the left, it only is for our imagination what is the meaning and why it is used. But in the fact, all those structures are stored in the memory. Then we find in the second level, use another 9 bits again. So basically, and in the fact, if we have 12 plus 4 times 9, then it is 36 plus 12, so it is 48 bits are decoded in those 4 levels of the tables. And because we do not need to add there the tables for those parts which are not used there, then we do not have so big waste of the memory to keep our all page tables. Okay, so there is a simple case for the Intel in 32-bit mode. In this case, it decodes 10 bits in single page table level. We have there a page directory base register, which is in the fact in the Intel called a control register 4, but it is not important. It is different for different architectures. Then we take the address from this and take 10 bits and multiply them by 4, but multiplication by 4 is only the shift to the left by 2. And we concatenate those two values and get the index into the page directory. And this index in the upper part, that area, holds the address of the next level of the page table. We take the another 10 bits and concatenate them with this start address, because all those addresses and all those fragments start on the address divisible by 4K. and get the actual physical address of the start of the page frame in the memory. And then we add the offset, and we are at the actual address in the memory. So basically this way we can translate any virtual address to the physical one. And in the case of Intel, there is interesting that for the 32-bit and even 64-bit system, they ensure that the size of this fragment is 2 power 10 in this case. But because we need to keep there a 32-bit values, then it is in the fact the size is 2 power 12, because it is 4K, 1000 multiplied by 4 bytes, or 1024 to be exact. So it has the advantage that even the allocation of the parts of the page table fits to the exactly single page frame in the physical memory. Okay, and a problem is that if we want to translate the address space, then okay, it is in the fact two-dimensional array. So basically there we have those this page directory, and it selects again the page table for each of these blocks. This is a translation. In the case that given data do not fit into the main memory, we mark it that it is not available, and then there is some page fault, and if there is a page fault, then operating system check if you have a right to access this area, and if the data are on the disk, and if they are on the disk, it swaps in the data from the disk. And okay, what is in the page table entries? So we need their frame number. So basically this address where we start with the given page in the physical memory. And we need there the information if a given address is valid. And we need there some access rights information if that page is available for everybody, if it is read-only, it is only for system, and so on. Okay, there are some remarks. We usually need even to keep their information if a given page has been accessed or not, because operating system needs to check which pages are not used for a longer time and use similar mechanism like that least recently used for the cache to kick out those pages, swap out those pages which are not used, because you need to find the space for new pages which are in use. So this is actually what is in the x86 in 32-bit mode in the directory. In page directory, we have there page base address, if it is valid. If it is not valid, then operating system can put there what it wants and basically use it to find data, for example, on the disk, corresponding data. Then there is information that it was accessed, if it is cached, if it is write through, write back, if it is available for the system, and so on, if it is read write or read only. And then this part points to the next level of the table. And again, actual page table entry, so that last level of the page table provides a physical address where a given page frame for a given page starts in the physical memory. If it is dirty, if there has been some change, so basically if you want to free the page which is dirty, then you first need to copy its contents to the disk or somewhere where is a backing store. Then if it has been accessed and so on, if it is used user system, if it is cached, and so on. So this is how it works. And the actual translation, if there is present a given page, is done by the hardware. So basically you access the addresses by the processor and your program, and you do not know that there is some page translation. But at the moment when you access the address, which is marked as invalid in the page table, then at that moment there is a page fault, which is caged by operating system, and operating system finds if your process has a right to access a given address, and if it has a right, it decides from which disk, file, and so on a data should be put into the main memory. It usually makes a space for the data by the freeing some another page. And when it sets up the page table to already point to the data which should correspond to the given page, then at this moment the state of the process is restored and your program continues. So program in the fact doesn't see anything except that there is some delay in the computation. And at that time the operating system puts a data there. And there is a more detailed description what happens, how we have that more level page tables. And the problem is that the translation, if you go through those 4 levels, then in the fact each access to the physical memory means in the fact 4 accesses to the page tables to do the translation. You see that you prolong each access 5 times. And okay, if you have cache, then you can check and store the information about those page tables even in the cache, and it is used. So basically the accesses to traverse the page tables are cached. But even in this case, it takes a long time. So what is used there? There is used again another kind of the cache, because it is probable that if you access some area of the virtual address space, that you will access it in the short time again. So for this reason, we add there so-called a translation look-aside buffer, which works exactly same as the cache. So basically, if you have a virtual page frame number, we first check if it is available the translation according to the tag to physical address. And if it is not, then we consult the actual page table and copy the translation to the translation look-aside buffer. So next time when we access the same page, we do not need to do the whole page table walk. We basically only look into this part. And there is that mechanism described how the CPU cooperates. There is a comparison what are the typical size of the pages and system and so on. There has been some extension because Intel was hesitant to switch to 64-bit for a long time, so he extended the physical address space to 16 gigabytes, even that the system was limited to the 4 gigabytes of virtual address space and so on. It is not so important. For the 64-bit system, we usually use such mechanism that there is a gap in the middle. So basically that the address has to be in the canonical form. The most significant bits of the virtual and physical address are in the fact sign extension of the address. Why it is kept in those 2 separate locations? It is done for this reason that usually those high addresses are used by the operating system and are not accessible to the user, and user has its area from the bottom. And when you add the next level, then in the fact you do not need to change much, because in this case only the user accessible region is extend up, and same for the operating system, which is extend down. So it is the mechanism why we use this. There are some description how, for example, we can check what is actual page size on the typical POSIX system. We can allocate even the memory to the page boundaries and so on. There is how we can check the sizes of the pages on the Windows. Sometimes we can use even the huge pages which allows a less translation and so on. This is the problems of the those hierarchical memory systems. Problems is at the moment when more processor starts to access the same data, it starts to be quite complex, and if you have read-write accesses to the common data, then the things start to be extremely slow. So there is a description coherency, consistency, but it is for the advanced computer architecture course already, inclusive, exclusive, and so on.